Multiplication of matrices. So multiplication of two matrices isn't an obvious process. There are a lot of numbers flying around. It all seems quite complicated until you actually just get into doing it, and then it really isn't that hard, and you'll find it becomes quite second nature with some practice. So we need to recall that the dimension or order of a matrix is how we refer to its size, and it's written as R times C, where R is the number of rows and C is the number of columns. So if we have a matrix, for example, with 2 rows and 3 columns, this would be a 2 by 3 matrix, or a matrix with order 2 by 3 or dimension 2 by 3. So the product of two matrices doesn't always exist. You can't multiply any two matrices together. You can only perform the multiplication if the number of columns in the first matrix is equal to the number of rows in the second matrix. Now that sounds as if it might be quite a complicated rule to remember, but once you learn how to do the multiplication, it will become quite clear when you can't do it. The numbers just won't line up properly, it won't work. But it's also quite easy if you actually write out the dimensions. So if, for example, we have matrix A, which is an m by n matrix, and matrix B, which is an n by p matrix, then AB exists because we're doing m times n, and we're multiplying that by n times p. So the multiplication is all okay because this number, which is the number of columns in the first matrix, is the same as this number, which is the number of rows in the second matrix. So those need to be the same in order for the multiplication to exist. Then these other two numbers, m and p, they actually give you the dimensions of the resulting matrix after you've performed the multiplication. So once we've multiplied these two matrices together, we will end up with an m by p matrix. Now another important fact with matrix multiplication is that it is not commutative. So generally, when we're talking about working with numbers, multiplication is a commutative process. You can do it in both directions and you get the same result. So 2 times 3 is the same as 3 times 2. For matrices, that is not the case. A times B is not the same as B times A. And in fact, one might exist and the other might not exist at all due to these restrictions on the dimension. So obviously, you need to be very careful about the order in which you multiply matrices. You'll see that when we see the process of actually doing the multiplication, that if you were to reverse the multiplication, you would be combining together all the numbers in quite different combinations. So you would certainly end up with a different result. Okay, so to find the product of two matrices, each row in the first matrix must multiply, and I use that word loosely, we're not directly multiplying, there's a sort of process to it, but each row in the first matrix must multiply each column in the second matrix. So it's rows times columns, rows times columns. Okay, let's get on to some examples so we can see how it works. Alright, so here we have two matrices, A and B. A is a 2 by 2 matrix. B is also a 2 by 2 matrix, so the multiplication is possible because those two numbers are the same, and the matrix that we end up with is going to be 2 by 2. Okay, so let's write these out. So we're going to have 11, negative 5, 2, negative 3, times negative 1, 6, 9, negative 3. Now our resulting matrix is going to be 2 by 2. I'm going to make it quite big, or I'll close it off once we're finished because I'm going to write out quite a bit of steps. Now I wouldn't normally write, I would do all the calculations in my head and just write down the answer. So sometimes it can be quite difficult in a written example to see actually what's happening. That's why it's important to sort of hear it explained or see it demonstrated. Okay, so each row in the first matrix has to multiply each column in the second matrix. So we're going to do top row times left column, top row times right column, bottom row times left column, bottom row times right column. That's where we're going to get the 4 numbers for our 2 by 2 matrix. Now when we do top row times left column, the result of that is going to go in the top left of our final matrix. Now when we say multiply, what I see in my head, and this is quite difficult to explain without me being able to move my hands around and show you, I see the row in the first matrix, this number 11 and -5 that I've got in this pink oval. I see that rotating around in a clockwise direction to sit vertically next to the column in the second matrix. So the 11 will be next to the -1 and the -5 will be next to the 9. And then what we're going to do is we're going to do 11 times -1, -5 times 9, and we're going to add those two numbers together. So multiplying this row times this column means doing 11 times -1 plus -5 times 9. Alright, so then we're going to have top row right column, and that's going to go in the top right. So we're going to do 11 times 6 plus -5 times -3. Okay, then we're going to have bottom row times left column, so that's going to go in the bottom left. 2 times -1 plus -3 times 9. And then bottom row times right column, 2 times 6 plus -3 times -3. Alright, so usually I would have done those calculations in my head and just written down 4 numbers as I went, but that's fine, we can work them out as we go. So sometimes it's worth writing out the steps because there are quite a few numbers and they can get big quite quickly because you're multiplying them together. So we've got 11 times -1, so it's -11 plus -45. So that is going to be -56. Here we've got 11 times 6, so 66 plus 15. So that is 81. -2 plus -27, so that's -29. And 12 plus 9, that is 21. And so there is the product, AB. So you can see if we had done BA would also be possible, the dimensions would work, but we would be combining these numbers in very different ways because we would be using the numbers in the first matrix, where here we've only used them as rows, we would be using them as columns. So we'd be using the 11 and the 2 together and the -5 and the -3 together, which we haven't done at all in this calculation. Similarly, in the second matrix, we've only used those numbers in columns, we would be using them in rows. So you're using all the same numbers, but you'd be combining them together in very different ways to produce quite a different answer. In fact, I challenge you to pause the video here and work out the product of those two matrices the other way, so B times A. Alright, but moving along here, let's have a look at a second example. So here we have two matrices again, A and B. A this time is a 3 by 2 matrix, and B is a 2 by 1 matrix. So this multiplication is possible because those two numbers are the same, and the matrix we're going to end up with is going to be 3 by 1. Okay, so let's set this up. So we've got 1, 4, 7, -1, 2, 3. We're going to multiply that by 9, 12. And we're expecting a 3 by 1 matrix. Okay, rows in the first matrix must multiply columns in the second matrix. So we can see how the dimensions here work because the width of this row is the same as the height of this column. So we've got two numbers in the row and two numbers in the column, which is what allows us to do the multiplication. Okay, so we're going to do 1 times 9. 1 times 9 plus 4 times 12. Then we're going to do middle row times only column. 7 times 9 plus -1 times 12. And then we're going to do bottom row times only column. 2 times 9 plus 3 times 12. Okay, so working those out, that is 9 plus 48, so 57. 63 minus 12, so 51. And 18 plus 36, 36 plus 44, 54. Now, if you want to, if there's a common factor, which I think there is in this case, 3 is common here, it is possible to take out the common factor of 3. So this would be the same as 3 times, what's that, 19, 17 and 18, but not necessary. So they're exactly the same, neither is more simple or less. Okay, let's do another multiplication. Alright, so here we have a 1 by 4 matrix multiplied by a 4 by 2 matrix. So again, this multiplication is possible because those are the same. And we're going to end up with a 1 by 2 matrix. So the interesting thing about matrices is because of what happens with the dimensions in the multiplication is you can actually start off with 2 quite big matrices involving lots of numbers, and multiplying them together produces a much smaller one. So in this case, we're only going to end up with 2 numbers, where here we've started with 12 numbers. So it just depends on the dimensions and how it all fits together. Okay, so we've got A, which is 8, negative 4, 2, negative 3, and we're multiplying that by negative 1, 6, 9, negative 3, 2, negative 4, 1, 7. Okay, and so we've decided that our resulting matrix will be 1 by 2. Okay, so we're going to do only row times left-hand column. So that's going to go in the left-hand spot of our only row. So I'm going to have to write a bit small here. We've got 8, actually I'm going to do the multiplications as I go. So 8 times negative 1, so that's negative 8, plus negative 4 times 9, that's negative 36, plus 2 times 2, which is 4, plus negative 3 times 1, which is negative 3. And then we're going to do only row times right hand column. 8 sixes are 48, plus negative 4 times negative 3 is positive 12, plus 2 times negative 4 is negative 8, plus negative 3 times 7 is negative 21. Alright, so then we can just work those out. So we've got negative 8 minus 36, so that is negative 44. Plus 4 is negative 40, minus 3 is negative 43. 48 plus 12 is 60, minus 8 is 52, minus 21 is 51/31. And so that is AB. Alright, lastly let's just have a little play around with the dimensions and the properties of multiplication and size. So A is a 2 by 2 matrix, B is a 3 by 2 matrix, and C is a 2 by 1 matrix. Determine which of the following exist and state the dimensions if they do exist. Okay, so A times B is 2 by 2 times 3 by 2. Okay, so this is going to be problematic because these numbers here don't match. So if we think about what's happening here, we've got a 2 by 2 matrix and we've got a 3 by 2 matrix. So because of the process of multiplication, rows times columns, you can see that you're going to have a problem here because you're trying to multiply 2 numbers with 3 numbers, and that's just not going to work. So that's why this restriction happens, and you'll see, even if you didn't recognize it in looking at the dimensions, if you drew it out like this and you started to go ahead to multiply it, you'd think, oh, hang on, something's not right here. This obviously doesn't exist. Okay, so AB doesn't exist. What about BA if we do the same matrices but the other way around? Remembering matrix multiplication isn't commutative, so it might work the other way. And in fact it does. A 3 by 2 times a 2 by 2. 2 columns in the first matrix and 2 rows in the second matrix mean that that is possible. So BA exists and is 3 by 2. So that 3 by 2 came from 3 by 2. Alright, AC. So A is 2 by 2. C is 2 by 1. So this exists. So AC exists and is 2 by 1. CA, so other way around, 2 by 1 times 2 by 2, well that's going to be problematic. This doesn't work here, and so CA doesn't exist. BC, so B is 3 by 2, C is 2 by 1, so everything's A-OK in terms of the multiplication. BC does exist, and it has dimensions 3 by 1. CB, so 2 by 1 times 3 by 2, that's going to be problematic. Only one column and yet 3 rows, we won't be able to multiply it together. So CB doesn't exist. So you'll see in each of these cases we're seeing examples of where the matrix multiplication isn't commutative. A times B doesn't exist, yet B times A does. A times C exists, yet C times A doesn't, etc. So it's also worth noting, though, that just because one exists, that doesn't necessarily mean that the other won't exist. That's just the case of these. If we're dealing with square matrices, if both matrices are 2 by 2, you'll be able to do the multiplication in both directions, but you'll get a different result both times. So now the key thing is to go and practice your matrix multiplication. Once you've done it a little bit, you'll find that the process really becomes quite second nature and you no longer have to really think about it. Good luck.